Now there are three diagrams. You've got bending, stretching and compressing on the left hand side of this slide. So have a look at the diagram. Have a look at this description on the right hand side. So you have bending is when a force is applied to a length of material away from some pivot. The bending force is applied to a point, area or volume that is some distance from a fixed portion of the component or structure to which the force is being applied. Bending can also result when. So complete the sentence. Have a look at the diagram on the left, where you've got two forces acting to the left hand side, and then you've got a single force acting to the center of the object. So how would you complete that sentence? And also, is the description correct? Okay, let's have a look at stretching. So have a look at the diagram and read the description. So stretching is when two opposing forces are applied from the center of the center, increasing the object's length. So is the circled word correct? What can be improved? So stretching is when two opposing forces are applied, is it away from the center of the object? Increasing the object's length. Um, all right, so write your own description of stretching. What could be improved? So have a look at the diagram. You've got bending, stretching, and compressing. So for stretching, what is the description of stretching? Compressing is when two opposing forces are applied towards the center of the object, decreasing its length along where the force acts. So again, have a look at the diagram for compressing and then write your own description of compression. Okay, so let me just read through the slides. So changes of shape. When a force acts on an object, the object may change shape by bending, stretching, or compressing, or combination of all three shape changes. However, to change the shape of a stationary object, there must be more than one force acting to do the following. So, bend an object's end past each other, for example, when an archer pulls an arrow back against a bow. Pull an object's ends apart, for example when a rubber band is stretched. Push an object's ends together, for example when an empty drinks can is squashed. Alright, so spring constant is a measure of the stiffness of a spring up to its limit of proportionality. Okay, so let's have a look at the graph at the bottom of the slide, bottom left. So on the y-axis you've got force, on the x-axis you've got extension in meters, so force measured in newtons. You can see that it obeys Hooke's law. So Hooke's law is F is equal to kx. Now in some slides you've got F equals minus kx. Now the minus just means that it is, if you've got a mass on a spring, then the weight will always act towards the center of the earth. So if you assume the direction is towards the center of the earth and you take that as positive, then the minus kx would be in the other direction. That's why there's a minus there. So the straight line in the force against extension graph is Hooke's law, because Hooke's law is F equals kx. And F equals kx, that says that the force applied is proportional to the extension. And if you were to write that as a mathematical equation, you have F equals kx, and that is a straight line. So spring constant is a measure of the stiffness of a spring up to its limit of proportionality. Now the limit of proportionality is where it stops being a straight line. However, the elastic limit, beyond the elastic limit, that's when it will not go back to its original shape. So the limit of proportionality does not necessarily have to be the same as the elastic limit. The limit of proportionality refers to the point beyond which Hooke's law is no longer true when stretching a material. The elastic limit of a material is the furthest amount it can be stretched or deformed without being able to return to its previous shape. Once a material has gone past its elastic limit, its deformation is said to be inelastic, which meaning it's plastic, so it won't go back to its original length. The higher the spring constant, the stiffer the spring. The spring constant is different for different elastic objects. For a given spring and other elastic objects, the extension is directly proportional to the force applied, so that is Hooke's law. So if the extension is doubled, then the force is doubled. This works until the limit of proportionality is exceeded. Okay, so the question is, what happens before the limit of proportionality? Question 2. An object can still go back to its original shape after it passes its limit of proportionality. Describe Hooke's law in words and the equation. 3. What is the difference between elastic and plastic? 4. Which part of the graph is linear and which part is non-linear? Okay, have a look at the diagram here. Is the bigger wheel spinning more slowly, and is it half the speed? So half the speed is the bigger wheel spinning um, half the speed, as in the rotational speed. When I say rotational speed, I mean angular velocity or angular. Yeah, I mean angular velocity. So, for example, if it's spinning 1 revolutions per second, that means it will go round once every second. Okay, so the question is the bigger wheel spinning more slowly? Um, when I say half the speed, so for example, if the smaller one is traveling at 1 revolutions per second, for example, then the bigger wheel will be traveling at half a revolution per second. Um, all right, so torque. Torque is also known as a moment or moment of force, and it is the tendency of a force to cause or change the rotational motion of a body. Um, and the equation is force applied times the perpendicular distance to the pivot. All right, so if you look at this gear, there's a large gear and a small gear. Now let's just say that the large gear has 4 times as many teeth as the smaller gear. So if the big one rotates 1 time, as in if it rotates once, um, then the smaller wheel will rotate 4 times. So gears are wheels with teeth that slot together. When one gear is turned, the other turns as well. If the gears are of different sizes, they can be used to increase the power of a turning force. So the smaller wheel turns more quickly but with less force, while the bigger one turns more slowly with more force. Cars and bicycles use gears to achieve amazing speeds our bodies could never match without help. Similarly, if one of the wheels is spinning anti-clockwise, let's look at the top one. If that is spinning anti-clockwise, the wheel at the bottom will spin clockwise. A larger gear will rotate slower than a smaller gear and have a greater torque, and the two gears will rotate in opposite directions. Alright, so let's answer this question. The diagram shows a spanner being used to tighten a nut. Calculate the moment being applied to the nut in the figure. Give your answer in Newton meters. This is 3 marks. So the question um, is asking for the moment, but remember the equation is the perpendicular distance of that force to the pivot. Um, so you've got a diagram here saying 25 centimeters, 15 centimeters, and 20 centimeters. Which of those measurements is perpendicular to the force? You can see that it is 20 centimeters, but remember you have to convert that centimeters into meters. So 200 newtons times 0.2 will give you 40 newton meters, and that will be 3 marks. Um, So if you look at the mark scheme, the moment is equal to the force times the perpendicular distance to the pivot. Perpendicular distance is 20 centimeters. You convert the centimeters into meters, and then you times those two quantities together. However, there's another way of doing it, but this uses trigonometry. Um, right. So um, if you look at the 200 newtons acting down. If you look at the smaller triangle, the 200 newtons is the longer length, and then can you see the right angle triangle? Let me pen here. So this triangle here that I've circled, the 200 newtons is the hypotenuse, and is the angle A is in between. So the angle A is in between these two, right? So that's angle A. That's angle A. It's in between these two. So if you okay, so if you know that's A, this is 90, that's 90, this is 90, and this whole thing is 90. So if this angle is A, that means that this angle is 90 minus A. So this 90 minus A is for, let me get this pen here. So this 90 minus A is for this one here. So that's 90 minus A, because the whole thing here is 90. If that is 90 minus A, and that's 90, then this angle must be A. So this is angle A, and this is angle A. So they are the same angle. Okay, so you're given the lengths 25 centimeters, 15 centimeters, 20 centimeters. So sine A is opposite over the hypotenuse. So in this case, sine A is 15 divided by 25, and cos of A is adjacent over the hypotenuse. So cos of A is 20 over 25. We want to work out the perpendicular distance of the force to the pivot. So this is the pivot right here. So here's the pivot, right? Here's the pivot. The force, if you want to work, because the perpendicular force is this one. We don't want this one here, the one that I've just highlighted. We want this one here, because that's perpendicular. So the perpendicular distance is this and this one here. Let me just rub this out. Okay, so how do we work out this part? How do we work out? So we know that the hypotenuse is 200, so this part is 200. We want to work out this part. So it would be 200 times cos A. And we know that cos A is 20 divided by 25. So the components of this force, perpendicular distance from the pivot, is 200 times 20 divided by 25. That gives you 160 newtons. Because we've just worked out the perpendicular force, and that is 160 newtons. If we times it by the distance of that perpendicular force to the pivot, we end up with 160 newtons times 0.25, because that's 25 centimeters, and you end up with 40 newtons. Okay. For part of the ride, the cyclist pushed on the pedals with a constant vertical force of 300 newtons. The simplified diagrams show the pedals in 3 different positions. Which positions, A, B, or C, gives the largest moment on the pedal? Calculate the size of the largest moment on the pedal in Newton meters. You can see that this one will be 0, because this is along the line passing through the pivot. You can see that this one's at an angle, so this won't give, and also this one says 14, and that says 16. So 14 is less than 16, so this will be less. So can you see that the answer is C, because 300 newtons is perpendicular to 16 centimeters. Calculate the size of the largest moment on the pedal, so you will just do 300 times 16 centimeters, but remember you have to convert 16 centimeters into meters. Alright, so this is the answer. The answer is C, and it's 48 Newton meters. Alright, this question. A gear with a radius of 0.1 meters is turned by a gear with a radius of 0.05 meters. The moment of the smaller gear is 20 Newton meters. Calculate the moment of the larger gear. Right, so the moment is equal to force times distance. 20 Newton meters, which is the moment, is equal to 0.05 meters times the force. You want to work out the force. So to work out the force, you divide both sides by 0.05, you end up with 400 newtons. Now, because of Newton's third law, it's the same force but in the opposite direction. So the moment of the larger gear will be the same force, but then you multiply by the distance, and in this case it's the radius, which is 0.1 meters. So it's 400 times 0.1, 40 Newton meters. All right, so let me read through this box. As one gear turns, the other gear must also turn. Where the gears meet, the teeth must both move in the same direction. In the diagram, the teeth of both gears, where they meet, move left. This means that the gears rotate in opposite directions. So the bigger wheel, which is at the top, is rotating clockwise, and the wheel at the bottom, which is the smaller one, will be moving anti-clockwise. Can you see here that where they meet, they will both move in the same direction? But the bottom is moving anti-clockwise, the top is moving clockwise. Okay, so the forces acting on the teeth are identical for both gears, but their moments are different. If a larger gear is driven by a smaller gear, the large gear will rotate slowly but will have a greater moment. For example, a low gear on a bike or car, if a smaller gear is driven by a larger gear will rotate quickly but will have a smaller moment. For example, a high gear on a bike or a car. You can have a look at this question. Again, this uses trigonometry. So here you have an aircraft nose wheel. The question says use moments to find the force acting on the link. This is a very hard question, but you're welcome to have a look at it. Find the vertical and horizontal components of the force on A, B, C, at B. Right, let's have a look at this question. This could be an exam question. Figure 2 shows a diagram of a compound gear train consisting of 4 gears A, B, C, and D. Gears B and C rotate together on the same shaft. So, if you look at the yellow box, it says when A rotates, B rotates. B is on top of C. When C rotates, D rotates. A rotates at 120 revolutions per second. RPM, because RPM stands for revolutions per second, and one revolution means that it goes round the circle once. Okay, so the question is, the input gear rotates at 120 revolutions per second. Calculate the rotational speed of the output gear. Now, the one with the smaller teeth will rotate faster, and you know that B is joined with C, and then if you look at D and C, D has a small amount of teeth, so therefore that will rotate faster. Right, so the answer. My answer is in the orange box on the right hand side. So the gear with the smaller teeth rotates faster. So the ratio is 50 divided by 20, so it's 3.5. So the one with the 20 teeth, that will rotate 2.5 times faster than A. And you know that A rotates at 120, so you times 2.5 and 120, you get 300 revolutions per minute. C will rotate at 300 revolutions per minute. Now the ratio of 25 teeth and 75 teeth with 25 teeth is 3. You know that B is connected to C, so gear D will rotate 3 times faster than C, because you've got 25 and 75 teeth. It's all about ratios. And then because you know that gear B and C are the same, B and C is rotating at 300 RPM, D is 3 times faster, so it's 900 revolutions per minute. Let's have a look at this diagram here. So you've got 4,000 newtons applied to the I don't know what that's called. It's 4,000 newtons to the instrument. That makes it turn. You know that the radius is 0.15 meters. So the moment of this force is force times distance, which is 600 newton meters. Is that correct? Yes, it is correct. Yes, so 4,000 times 0.15 is 600 newton meters. Now this is connected by a string. To find out the gear ratio, it will be 0.3 meters divided by 0.015. Is that too? Okay, so this point's incorrect. That should be 0.15. But the gear ratio is 2 to 1. So that means that it will have twice the moment. So the one with the bigger wheel will have double the moment of the smaller wheel. So if you do 2 times 600, you get 1,200 Newton meters. Alright, this question. Calculate the speed and torque of output shaft of a single gear train where the number of teeth on driver and driven gear at 40 and 20 respectively, and driver gears rotating with 100 revolutions per minute and 10 Newton meter torque. Remember that torque is just a moment of force, and remember moment of force is the perpendicular distance of the force from the pivot. Okay, so the answer is 200 revolutions per minute, because you know that the one with the smaller wheel will rotate faster, and the ratio is 2 to 1, because the number of teeth is half, so you must double the speed. So it's 200 revolutions per minute. And also the torque will be half, because the radius is half. And because the radius is half, then the moment is half. Okay, so you should know what torque is. Let's have a look at this diagram here. If the one on the left, 15 teeth, has a revolution of 3.73, you need to work out the ratio, and 56 divided by 15 is 3.73 times bigger. So that means that the revolutions will be 3.73 times smaller, because remember it takes longer for the bigger wheel to rotate once. So driven divided by driver is 56 divided by 15, which is 3.73. The circular design of gears allows for continuous rotation. You can pause this and have a look for yourself what this means. Right. Levers such as this one make use of moments to act as a force multiplier. They allow a large force to act upon the load than is supplied by the effort, so it is easier to move large or heavy objects. Okay, let's have a look at this question. A non-uniform rod AB has length 3 meters and mass 4.5 kilograms. The rod rests in equilibrium in a horizontal position on two smooth supports at P and at Q, where AP is 0.8 meters and QB is 0.6 meters as shown in the diagram. The center of mass of the rod is at G. Given the magnitude of the reaction and the support at P on the rod is twice the magnitude of the reaction at the support at Q, find the magnitude of the reaction at the support at Q on the rod and the distance of AG. Alright, now because it's in equilibrium, you know that all the upwards forces is equal to all the downwards forces. So P plus Q is equal to W, but you know in the question it says P is twice the force at Q. So P is equal to 2Q. If you add 2Q and Q, you get 3Q. So that's 3Q. And you know that 3Q is equal to the weight. Now let's take moments. Now you can take moments about anywhere. If you take moments about A, let's work out the clockwise moments. Now the only A force is acting downwards is the weight. And can you see that's going to go clockwise? If you were to take pivots about A, and their force acting downwards is at G, can you see that it will go around A in a clockwise manner? If you look at P and Q, it will go anti-clockwise. Now you also know that the sum of anti-clockwise moments equals the sum of the clockwise moments. Right, so the clockwise moment is equal to the weight times the distance of A to G. That's the clockwise moments. And can you see that you've got two forces that's going to go anti-clockwise? So you have 0.8 times 2Q, and you add 2.4. Why is it 2.4? Because it's 3 minus 0.6. So you have 2.4 times Q. And then you add them together, because that's the sum of the anti-clockwise moments. If it's in equilibrium, then the sum of the anti-clockwise moment is equal to the sum of the clockwise moments. Okay, so now you have two equations. You've got 3Q equals W, and you have 0.8 times 2Q plus 2.4 times Q. You should have a simultaneous equation. However, you know that the mass is 4.5 kilograms. So how do you work out the weight? So the weight is equal to the mass times 9.81. So you know the weight is equal to 44.145 newtons. Put that into the equation 3Q equals W. Then you can work out Q, because then you can divide both sides by 3. You end up with Q is equal to 14.715 newtons. And then how do you work out X? Well, once you have Q, where are we? X. Okay, so X is equal to 4Q divided by W, because it's from the top here. So from the top, let me go to here. Because from, I'm trying to find my pointer. Where's it gone? Right, I was there. Because from here, you've got Wx equals 4Q. Because you've worked out what Q is, you put it back into this equation, and you know that W is 44.145. So 44.145 X is equal to 4Q. Hold on, that doesn't help. Alright, okay. Because you've worked out Q and you've got W, you've worked out Q is 14.715, W is 44.145. Put that into the equation, you should end up with X is equal to 1.33. Alright, let's have a look at this problem. So you've got 18 newtons is applied to a gear wheel of radius 1 centimeter, which is A, the circle A, the gear A, to turn another gear wheel of radius 2 centimeters, radius B. What is the moment of force on A wheel and B wheel? Right, so the radius is 0.01 meters for A, and you know that it is 80 newtons. So 80 newtons times the distance to the pivot is 0.8 newton meters. And then for B, because it has the same force but equal and opposite, 80 times 0.02 is equal to 1.6 newton meters. Alright, have a go at this question. Which of the following is in equilibrium? So remember, you've got to find the anti-clockwise moments and the clockwise moments. Are they the same? So for part I, work out all the clockwise moments and work out all the anti-clockwise moments. Are they the same? If they are the same, it is in equilibrium. If it's not the same, it is not in equilibrium. Work at this one. So a force of 40 newtons is applied to a spanner to turn a nut. The perpendicular distance is 30 centimeters. Calculate the moments of the force. The second question, a force of 15 newtons is applied to a door handle 15 centimeters from the pivot. Calculate the moment of the force. Alright, answer this question. So A, what are the units on the y-axis? What are the units on the x-axis? The gradient of this graph is, complete the sentence, use the formula F equals kx. Above the elastic limit is the what region, so explain what that region does. And above the linear region is where Hooke's law is not what. So what is that missing word? Alright, the diagram shows a compressed spring with a spring constant of 5 newtons per meter and 480 joules of energy in its elastic potential energy store. What is the compression? Calculate the compression using the equation. Alright, so can you answer this question? So the photograph shows a man dropping an egg inside a padded box from a height. He is investigating to see if the padding stops the egg from breaking. State the type of energy which the egg gains as it falls. The weight of the egg is 0.6 newtons. Calculate the work done on the egg to lift it up by 20 meters. State the unit. Now the equation is potential energy is equal to mgh. Okay, so the work done on the egg is, and what is the units? The velocity of the container is 18 meters per second as it hits the floor. The mass of the container was 0.5 kilograms. Calculate the momentum of the container. Okay, answer this question. Explain moment of a force and its SI units. What is the principle of moments? Figure 5.1 shows a balanced uniform beam supported at its center. What is the ratio of mass A to mass B? Part B. Figure 5.2 shows a massless beam of length 1 meter pivoted at P. A mass of 2 kilograms rests on it at 60 centimeters from P. At Q, it rests on a support which exerts a force R. What is the magnitude of R? Figure 5.3 below shows a non-uniform tree trunk of weight 1000 newtons resting horizontally on two supports at Q and S. The center of mass of the tree trunk is at R. What downward force must be applied at P to lift the tree trunk just clear of the support at S? You've got four options. Is it 500, 750, 1000, or 1250 newtons? Figure 5.4 shows the same vertical force of 200 newtons exerted by a cyclist on the pedal of a bicycle in three different positions A, B, and C. State the position A, B, or C in which the force exerts the largest moment about the pivots. Give a reason for your answer. Figure 5.5 shows a support for a leg in plaster, and figure 5.6 shows a simplified diagram of the forces acting on the leg. Calculate the force F needed to keep the leg in a horizontal position. Figure 5.7 shows a person supporting a book between his fingers and thumb. If the point of contact is at the corner of the book and the weight W of the book is 10 newtons, calculate the moments of the force provided by A. The weight W of the book about the points of contact. A heavy uniform plank of length 3 meters is supported by two forces F1 at 0.25 meters from one end and F2 at 0.50 meters from the other end, as shown in figure 5.8. Calculate the ratio of F1 divided by F2. And question 7. A uniform meter plank XY of weight 200 newtons is freely hinged to a wall at X. A man of weight 500 newtons is standing 20 centimeters from the wall. The plank is held horizontally by a force F acting from Y as shown in the diagram. Calculate the magnitude of the force F.